So today's two lectures are going to be about topics from cohomology. And since I'm talking about polycyclic groups, it's going to be cohomology of polycyclic groups. Well, first of all, I thought, I'm not quite sure, I haven't been here for Graham's lectures and Alexander's lectures, but I thought I'd recall the basic definitions to begin with. So cohomology is a wide field. You have a lot of different aspects, a lot of different things that run under this name. In this case, I'm going to look at this type of cohomology of groups in general. So you start off with a group and a G module, M, and then first of all you need to define the n-fold direct product of the group with itself. So it's going to be a much larger group then. Then you have the space Cn of G with the module. That's just all maps from this direct product into the module, with the additional restriction that the image should be 0 if one of the inputs is 1. This is not strictly necessary, but it makes it a little bit smaller to begin with. Right. And then there is this map, alpha n, going from Cn minus 1 to Cn, and has a sort of technical definition, as I've written up there on the slide. So yeah, how can you look at these things? So if you want to, Cn is, well, you can take one of these maps from Cn, gamma in Cn, and this would correspond to the list of all images on all elements of G to the n, right? List of images, and therefore this Cn, Gm, can be identified with a huge space over M, G, order of G minus 1 to the n. So in the end, Cn is a huge linear space over M. If your M is a vector space to begin with, then this also could be identified with a vector space in a rather large dimension. If your group is finite, then at least a finite dimensional vector space. If the group is infinite, then all hell breaks loose, really. And alpha n is a linear map then, or can be considered as a linear map. Okay. So now we want to compute these three objects listed down here: cocycles, coboundaries, and the quotient of the two. The cocycles are a kernel of one of these linear maps. Zn is the kernel of alpha n plus 1. Coboundaries are the image of the smaller alpha n. And the nth cohomology group is then the quotient of the two. You have to make sure, of course, or you would have to prove that the coboundaries are a subset or subspace of the cocycles, but this has been done long ago, so we all know this is actually the case, and therefore you can write down the quotient, and that's the cohomology group. Now, since alpha n is a linear map and Cn is a linear space, in principle, as long as the group is finite, this can be computed by definition. It's just not going to be very practical. And if n grows larger, then these spaces are soon going to be so huge that you can't do anything. Now, yeah, Graham's HAP package is perhaps one of the major sources for computing these things, right? In lots of different cases. And what I'm going to do here is a much smaller thing than what HAP can do, really, but perhaps in a more efficient way. I'm going to consider the case that the group in question is polycyclic, can be infinite again, or finite or infinite, and we want to have some efficient methods to compute at least the small dimensional cohomology groups. So the dimension of the cohomology group is this n, and at least the small dimensional ones we want to be able to compute even if the group is an infinite group, and therefore this basic approach here is just not going to work anymore. All right? Okay. Well, let's have a look at the easiest of all cases. That's dimension 0. Dimension 0, B0 is going to be trivial anyway. It's not really defined. So we look at Z0, the cocycles in this smallest possible case. That's really comparatively trivial, because if you write down the definition for Z0 in real words without this linear map, then, well, you figure out that you just have to compute the fixed points in the module under the group action. All right, and now let's translate this to somewhat more computable things. This is my little lemma as written up there. So we can suppose that we have a vector space as a module. That's the standard case. Either we have, well, the standard cases are that you either have a module over a finite field, so often occurring. Perhaps I should note this. Either M is a finite field and to some dimension, or M is the integers, free module over the integers, or sometimes can be a rational space. Those are the three cases which have lots of applications and therefore turn up quite often. So in the first case, in the last case, you have a proper vector space. In the middle case here, it's a free module over the integers, usually also quite good to handle. All right. So this is what M usually is, a d-dimensional vector space over a field, or perhaps a free ZD module could also be the case. Now G is acting on this, so there is a homomorphism from G to GL DFP in this case, or GL DZ in the second case, GL DQ in the third case. That's what the action tells you, and since it's a homomorphism, this can be described in a quite compact form. Just need to write down the images of the generators of G, and that tells you how the homomorphism looks like. Right, so we take up a set of generators for the group. That's x1 up to x whatever, m. Our homomorphism is defined by the images of these generators. That's y1 to ym. And I need the identity matrix. And then Z0 is the intersection of the kernel of a bunch of matrices, really. So if you want so, you can say that Z0 can be obtained as the null space of a matrix. And the matrix 0 is just by concatenating the matrices that you get. So it's the matrix Y1 minus the identity, and then you have Y2 minus the identity, and Ym minus the identity. That's a matrix over your, which can be the finite field, the integers, or the rationals. And the dimension of the matrix is also given as D times MD. Okay, D times MD. And Z0 is the null space of that. All right, so I haven't assumed anything about the group except for that it's finitely generated. And really, this is all that I need for this easy case. But it's sort of setting the scene, right? Instead of computing the null space of this huge alpha 0 map, try to find a smaller representation of the whole thing and compute the null space of that. That's the general idea that is followed up in all the dimensions. So you want to define your spaces as null spaces or images of matrices, but perhaps not quite as big as the one over there. That's the general idea that one follows up here. No, it's just a finitely generated group, and then it would work. It must be the same in HAP, no? So yeah, do I recall lots of things that you have done already, Graham? I'm not sure. Okay, so this is dimension 0. Huh?
You were presenting it a little bit differently than you.
Yeah.
Much more practical.
Well, Graham tried to do much more than I did, I would guess. Since you're always looking at all dimension at once, it's a different story, really. Whereas I just try to do little things. Anyway, 0, and yeah, all fairly easy, isn't it? Dimension 1. All right. So again, dimension 1. Now we have maps from C2 to C1. Want to have kernel and perhaps image of all of this. So Z1 consists of maps from G to M. And well, we need again, or we would like to have again, a description in the same form as for Z0. So at the first step, we need to somehow make it smaller. Instead of looking at images of all the elements, that's too much. In particular, if the group is infinite, you can't do that. So you need a smaller representation of Z1 that is actually computable. And the first lemma there gives you this representation. You again take a set of generators for your group, and you define a map, I've called it rho, from Z1 to a space over M, an M-dimensional space over M, and you just take the images of the generators. Now, cohomology, these maps alpha n, they are not group homomorphisms, and therefore it's not clear at all that the images of the generators are sufficient to describe your cohomology setting. It only works for the one-dimensional case, because that's still fairly simple, and it, well, the definition of cocycles in Z1 follow the rule that gamma of a product, G times H, can be computed as gamma of G or acted on by H plus gamma of H, and therefore taking the images of the generators is actually sufficient to describe the full cocycles. Okay, so this gives a representation of Z1 injective. Okay, so instead of describing the elements of Z1 by tuples for every element of G, I can now describe them by tuples for only the generators. And that's a huge, it's very important to understand this. Okay, we have a small description. Now we want to be able to determine the image of this row. And that's the next lemma. So we again suppose that M is a vector space over a field now. And I have to suppose that the group is finitely presented. So the next dimension, every time when I go up one dimension, I have to have more restrictions on the acting groups. But well, in this case here, I now take finitely presented, meaning I have generators x1 up to xm and relators r1 up to rl. And M is the same form as before. Then this here says there is a matrix A1. I'm not going to tell you exactly how it looks like. It has the parameters, it's over the field or K, and has parameters d times M times d times L. So the relations somewhat play a role in setting up this matrix A1, so that Z1 corresponds to the null space of this matrix. Right. Now, Z1 can be computed from the presentation by pushing images on the generators through these relations. I think it's going to be fairly technical at that point, and I'm not sure whether I should go into too much detail here. Everybody is smiling, the people who know what I'm talking about. Yes. So really the broad idea is that you take potential images on x1 up to xm, and then they have to satisfy these relations in some form, and therefore you push it through and get conditions. For every relation you get a set of conditions on your cohomology map. You list all these conditions in the matrix, fairly similar to this A0 case, and then you get a huge matrix, and Z1 is the null space, or this phi of Z1 corresponds to the null space of this matrix. Now still, if you consider the original definition of alpha n, this here is a huge improvement in size compared to alpha n. Now instead of having the group order in the game, I now have the generator number and the relation number, but both of these are going to be usually fairly small in comparison with the group order. In particular, if the group order is infinite, this can still be easily a that's actually computable. Okay, now I have A0, and Z1 can be interpreted as the kernel of A0. I have A1, that kernel of that gives me Z1. And B1 can, in fact, be interpreted then as the image of A0. So the image of A0 will be something of dimension m times d. The kernel of A1 is going to be something of dimension m times d. And that fits together. So in this form, as image of A0, kernel of A1, I can actually then get B1 and Z1. So perhaps I list this here. So Z0 corresponds to the kernel of A0. Z1 is the kernel of A1. Whoops. And B1 is the image of A0. And as it happens, these things fit together well enough so that this actually presents then a representation of H1. I think I've listed this as a summary on my slides here. Okay. So Z1 sits inside k to the dm, kernel of A1. B1 sits inside k to the dm, image of A0. H1 then corresponds to the quotient space of the two objects. And, well, it doesn't really matter. You can do it over a vector space or over the integers. In both cases, you have to compute kernels and images of matrices. For fields or vector spaces over fields, that's the algorithm of Gauss. And for the integers, there is an easy variation of that that will give you the same over the integers. So it's, in the end, it then boils down to the algorithm of Gauss to compute all these things once you have the matrices set up. All right. Now, yeah, in group theory, there is a reason why one wants to compute all these things, and that's also listed here as a lemma. Very important application of this cohomology in dimension 1 is lemma 6. Well, in some sense, an the applications, but never mind. So if M is an elementary abelian normal subgroup in a group H, and it has a complement, G, then the group Z1, G of G and M, corresponds one-to-one to the set of all complements to M in H. And this is actually fairly practical. So you have your group H, that's a split extension of M by G. And G is given, say, by generators x1 up to xm in H. Now write down complements, say G alpha, as taking the generators and adding on the images under the cocycle alpha, like this, xm alpha xm for each alpha or m, right? Then another complement, 2m in H. And again, this representation of Z1 is very practical in this case, because not only it's better to compute than by definition, it also gives you this application neat and easy form. So if you have one complement, you can write down all the others just by taking the images or the elements of this Z1 in the form that we have computed it, right? To all complements. And also it's known that two of these complements are conjugate in H, if and only if the difference of the cocycles lies in B1. So this is in effect what part B is expressing here. H1 then corresponds to the set of our conjugacy class representatives of complements. So two complements are conjugate if their corresponding cocycles, their difference lies in B1. This sort of
elementary abelian, that means that it's a vector space that's not over Z.
elementary abelian means it's a vector space over a finite field with p elements, right? But it doesn't really matter. You could also do it for the integers in the same form. And could also, I mean, if you do it over the integers, then finiteness questions come into the game. It's not clear that the cohomology group is still finite then. And then, well, if you have infinitely many things, then life becomes more difficult. But over a finite field, this here is fairly easy to do. And also this gets used, this is a sort of basic fundamental thing that gets used in many algorithms for finite groups in gap. So there are many things where this sort of approach is used. For example, if you want to compute, it's a standard question. You have a group and you want to compute all of its subgroups. That's usually a huge mess. So you don't really want to do this. Instead, you want to restrict to conjugacy classes of subgroups. It gets a bit better then. And if you want to do that, then, well, this here actually applies and can be used to do this in a very neat and easy manner. So I think Alexander has implemented this 1,000 times already, right? So you're using this all the time to deal with. It comes again, oh dear, yes. So you hear it.
You didn't like it, now you don't like it later.
Let's see, okay. So here we go. This is the one-dimensional cohomology and one of its most important applications in group theory. But also these things have interest in their own right. It's not only because of this application here. Right, and then the most daunting step, dimension 2. Now it gets even more complicated. So for dimension 0, we found a nice representation. For dimension 1, we found a nice representation. The next step would be for dimension 2, we somehow have to try to do the same. And in that case, you now really need, well, not strictly, but it's easier if you have a polycyclic presentation and try to use that for your computations. Now, the first setup steps are for arbitrary presentations. Well, yeah, let's go through it then. The group Z2 consists of maps from G cross G to M. Okay. We want to have a nice description for it. We take a finite presentation for our group and a vector space for our module. Vector space over K, over a finite field, over Z, or potentially also over Q. Lots of things are possible here. Now, the group of two cocycles is in correspondence to the extensions of G by M. So, well, I need a, where do I have this thing to clean the blackboard? Right. Okay, now the cocycles correspond to extensions. So I have something like 0 goes to M, goes to an extension, goes to G, goes to 1. And yeah, this corresponds to an cocycle in Z2GM. And if I look at extensions of this finitely presented group by this module, then I can describe them by generators. Well, I take the generators of the finite presentation plus generators for M. So that would be x1 up to xm for the group G, and y1 up to yd for the module M. So this here corresponds to G. This here corresponds to the module. And now I want to think about how can I describe this H in terms of a presentation. How could this possibly work? And it works by modifying the relations of the group in these forms there. So you have to have 3 types of relations. The first one is a modification of the relations for G. Right? The relations itself might not hold anymore, but with a simple modification in the module, you get a new relation that now holds for your group H. Then you need to know how the group G acts on the module. That's the second type of relation. And thirdly, you need to describe M as an additive group. So you need to tell, well, the generators of M commute with each other, and perhaps they have an exponent. So you just write down relators describing M as additive group. So these 3 types of relations are sufficient to describe your extension in terms of generators and relations. Now the third type of relations is completely independent of this alpha. It just describes M as additive group. The second type of relations is also independent of alpha. It describes your module structure, G acting on M, and well, that can also be determined without knowing what alpha is. So it's only the first type of relations that has to do with alpha. So in effect, it's these right-hand sides of the first relation that tell you what alpha is. And that's the way in which we are going to represent the elements of the second cohomology. We take the relations of the group G and write up what we need as right-hand sides for them to turn those relations into relations for the extension corresponding to the cocycle. So this is the compact representation of Z2 if you want to compute this in gap. Right, so this is all fairly technical, but there it is. Cohomology is a bit technical. So I've written it up on the slides, I think. Relations of type 3 and type 2 are independent of the cocycle. It's only type 1 that we need. And if M is abelian, then each of these tails that we have here, these TIs are often called tails on the relation. They correspond to a vector over the field K. K is then whatever determines M. And concatenating all these vectors for the different relations leads a long vector, and that's now our way of representing Z2. Right. This can be done for, up to here, it can be done for every finitely presented group and every abelian module that you have. But now we want to compute the image of Z2 under phi. And one way of doing that is for polycyclic groups, where you can set up a matrix again. So now it's going to be a matrix called A2. That is a matrix over the ground ring or field K, and it has dimension dl times dk. So I certainly want, yes, dl times d small k, and k is not described so far. So for some k, and well, the image of Z2 under this representation phi is the kernel of this matrix again. So Z2 is the kernel of A2. B2 can be obtained as the image of the previously computed matrix A1. Again, these fit nicely together. This here has an image in dimension dl. This here has a kernel in dimension dl. You just have to figure out that all of this corresponds nicely, but it does. And then you get a representation for H2 as a vector space quotient in K to the dimension d times L. Now, a few things that you need to know about this. You know, in dimension 1, we have actually proved that this representation phi is an injective map. So it gives you a proper representation of Z1. Here I have not done anything like that. And in fact, it's also not true. This is not necessarily injective. But the kernel of phi sits inside B2. That's an important fact. Therefore, H2 is isomorphic to the image of Z2 under phi modulo the image of B2. So it's not a proper representation of the cocycles, but it gives you a proper representation of the quotient of the cohomology H2. All right. Again, I have not told you how to compute A2. Well, I haven't told you either why we need polycyclic groups, have I? So for the computation of H2, I use the fact that I have a polycyclic presentation.
But you told us what A2 is,
No, I didn't. Because that would, it's just, it's a technical horror, really. I don't know whether you want to understand this in a lecture. You rather go and read it up in a paper, I would guess. But you know, so what happens if G is polycyclic and you extend it by something elementary abelian or something which is ZD, then you get a polycyclic group again. So H is going to be also polycyclic. And well, if I start up with a polycyclic presentation for G, this abelian thing certainly has a polycyclic presentation. I combine these two and get a polycyclic presentation for H. And now there comes this business of confluence. I will go and set this up in a quite generic way. Oh. Okay. So I combine this. It gives me a fairly generic polycyclic presentation for H. And this is a polycyclic presentation for an extension if and only if it's confluent. So I run a generic confluence check over this presentation, and that gives me conditions that need to be satisfied. I collect these conditions, and that is my matrix A2. Perhaps I can write a little bit about this. So I have a presentation in these x1 to xm, y1 to yd with polycyclic relators or relations. And well, what I wrote up there really gives me a polycyclic presentation where only the TIs are not defined. I take them as indeterminates and run a confluence test on this presentation, including indeterminates. And this confluence test will then give me conditions. It has to be satisfied that I will get linear conditions on these TIs that have to be satisfied for each cocycle, and therefore I get my matrix A2. I call these confluence conditions. Now, confluence testing is a fairly technical business, and I think Alexander perhaps does it. Fine. So you'll see it later in more detail. This year is the first brush up about it. Okay, what else is on this slide? Yeah, confluence of presentations. Come into it. Yeah, here is one of the main applications of the second cohomology group in group theory. So the reason why this is so important. Yeah, the elements of H2 correspond one-to-one to equivalence classes of extensions of G by M, right? So you get, if you run over all possible elements of H2, you get certainly every isomorphism type of extension. You get them even several times. So equivalence classes are a slightly weaker notion than isomorphism. So in effect, you get all of the extensions of G by M up to equivalence, first of all. This is very often used if you want to construct groups of a certain type, or if you want to classify groups. Say, the construction of groups in the small groups library, that depends fairly heavily on this sort of approach. If you want to write down all groups of order, I don't know, 24 as an easy example, you run over all numbers that divide 24 and need to have the groups of those orders, and then you start this extension business in a sort of well-described form and list extensions. That will give you all of the groups of order 24, certainly. It will give them to you probably several times because equivalence is weaker than isomorphism. So the final step in such a classification then is to reduce to isomorphism. That's a standard approach to constructing groups. And it's used heavily in the in the construction of the small groups library, for example, and various other circumstances as well. So yeah, if you want to use it then, there is the problem that you need to reduce from equivalence classes to isomorphism classes. And that is well known in group theory as being one of the very, very difficult steps. If you start off with this type of extension theory, then you have a nice reduction that you can use, and that is using compatible pairs. So the compatible pairs form a subgroup in the direct product odd G times odd M. It's just the pairs of elements that are compatible with the module action. And this subgroup of compatible pairs then acts on H2. Two elements in the same orbit of this action yield isomorphic extensions. So this is actually some feature that you can use in this game of constructing extensions to reduce from equivalence classes to somewhat smaller output that eliminates a number of isomorphic copies right away. And in certain cases, this is even sufficient to solve the isomorphism problem for extensions. So this is not completely clear, but it tells you the main ideas that sit behind that. So you want to use constructions of H2 for constructing extensions, and well, using automorphism group actions is going to help with reducing that towards isomorphism types. Okay, so I have have a few more minutes, and I thought we have another gap session perhaps, and I try to tell you how this all looks in gap. Let's see. I think it was right here. So let's look at some of these cohomology groups. So now you can certainly start, well, you need to get yourself a group and a module. One module that you can always easily get is the trivial module. Otherwise, you need to do some computations before to get a module. Let's have just a look at that. So we start here with the dihedral, infinite dihedral group, as we have seen that yesterday. So this is this group where first generator has order 2, second generator has infinite order, and the conjugate of the second by the first is the inverse of the second. This is this nice matrix group that we have seen yesterday, and we are trying to use it for cohomology computations now. Now we need to get a module. As I say, the trivial module is always easy to write down. So describing a module in gap means that for every generator of your group, you have to write down what the acting matrix is, right? It's using this idea here that you have a homomorphism from your acting group to GL over your space, and you describe this homomorphism by writing down the images of the generator. Since it's a homomorphism, that's going to be sufficient. So let's see. You take generators. In this case, I could just tell you what IGS means. It's just a form of accessing the generators corresponding to the PCP presentation in a polycyclic group. And then M, you take these IGS generators. Each of them, in this case here, gets mapped to an identity matrix, and I thought we'd take a two-dimensional one over the field with two generators. So now you have two matrices in a list, and if I display them, gap has a rather intrinsic way of describing matrices over finite fields. You can display them and you see it's just identity matrices. Now for cohomology computations, I need to encode the presentation of my group in a nice form. And the way in which I do it for polycyclic groups is I pre-compute these encodings. And that's the bizarre command CR record by Mats. If you, I showed you once, I think, and it's going to set up a record that actually produces or combines all kinds of information that I need in cohomology computations. So it starts with the information that this is actually a trivial module, so the action is trivial, the characteristic of the field is 2, the dimension of the module is 2, and then I look at relations of G. Now what I'm not sure whether I want to tell you anything about it. This here is telling you what relations of G are used in which ordering. Then I have a presentation for G. This is the group I started with. I have the field again. I have the acting matrices and their inverses. This looks like redundant information, but I computed a priori since it's used a lot in the computations, and therefore I would like to have it pre-computed and not done it all the time on the fly. So this basically encodes the module and the presentation of the group. And now I can start.
What does the CR stand for record? Cohomology?
Yeah, something. I've made up the name about 20 years ago. I don't know. Sorry? Well, this here is usually if you just compute extensions or complements, you won't see it. It's only because you are here in the cohomology workshop that you have to have a look at it.
But the C must be cohomology.
Yeah. Whatever. So now, one coboundaries and one cocycles. Let's start with cocycles. One cocycles CR of this record can be computed, and well, it's a finite field matrix. If you display it, you now get a 4x4 matrix out of that represents your one cocycles. Now you know a little bit more about what this is supposed to be. This is one cocycle, so it's going to be the kernel of A1. The kernel of A1 has to be a matrix, has to be of dimension d times m. M is the number of generators of your group, it's 2. D is the dimension of the module, is 2, so it has to be over 2 times 2, so 4. Yes, so it's a 4-dimensional space, that's fine. And it's given to you by generators, or a basis of this Z1. So this is really what it is. And you can now understand a little bit better what the output of this function is. It has to be 4-dimensional over your given field. The field is the field with 2 elements. And well, it tells you basically that everything is possible as cocycle, because you have the full space as result. And one coboundaries. In this case, I take the basis right away. Why not? One coboundaries. Well, okay. It's the empty. It's the trivial space with trivial basis. So you can now read off that your cohomology, the second cohomology, is going to be 4-dimensional over the field with 2 elements. And it also gives you a quite explicit representation for these coboundaries. Now translate from coboundaries to complements in the application that this has quite readily if you want to. Right, now this was a finite field computation. You can do the same over other fields or in the integers. If you want the integers, you don't give any field there, just the identity matrix 2 by 2. Then you can do the same computation over the integers. Now we'll tell you the characteristic of this business is 0. For the rest of it, this record is much the same as before. And, well, one cocycles of this is now trivial over the integers. There is not so much. One coboundaries has to be trivial again as well. Yes, it is. All right. So here it goes. One cohomology. Feel free to ask questions if you have any. Sorry?
What is the
GF2 in GAP, that's the field with 2 elements.
Okay.
It's F2, Galois field with 2 elements. And it has this strange way of describing elements here in this. So 0, yeah, let's have a look. Elements of GF2. There are 2 of them. Z2 is a primitive element of F2. So you have the 0, that's this here. and the one that's here. And if you take a larger finite field, you will find this is the standard way of describing it. So you always have the 0, and then the others are powers of the primitive element. This is the way in which the finite fields and its element are described.
Wait.
Yeah?
Oh, I see. Z5 is the primitive element.
Yes.
I
You-
guess Z2 is also the primitive element, so Z2 is also equal to Z2 to the 0.
What is it?
Yes.
Ah, yes, yes, yes,
But
yes.
if you ask for Z2 in gap, it points Z2 towards 0.
Oh, okay.
So it's
That's,
it's
I mean, if you say Z2, then it still says Z2.
Yeah.
Okay, great. At least that's consistent.
Yeah, I mean, it gets more complicated if you look at finite fields of, I don't know. This laptop is getting at me. I don't know. I need to speak to a Mac expert about it. If you look at larger finite fields, say of order 25, it's actually getting more complicated. But there is a very clever representation of finite fields in gap that allows efficient computation. That's the reason why this is slightly irritating when you try to look at these elements. But for computations, I can assure you, it is very, very practical. So, yeah, you just have to adjust yourself to this type of printing. Okay. Now,
So the Z5 in those elements is actually equal in gap to the Z5 in GF5.
is it?
Yes.
It is, okay, that's good.
And that is deliberately, that's why it is represented this way. That the fields naturally, in the same characteristic, they naturally equal each other.
So they're all in one
Yes.
algebraic
Yes.
closure.
Yeah, so if you take, say, Z of 25 plus Z of 125, you can do this, it will be represented as something of a Z of 5 to 6.
There is actually quite a sophisticated theory behind it, this business with convey polynomials. But
Then, yeah, and this representation goes under the name of set logarithms.
So, despite the fact that it looks so strange, it is actually well thought out. Right, but here we only want to use this type of thing. What else did I do? Perhaps I do, before the break, only a few more computations of the same sort of type. I could do, let's have another look at cohomology. So we're looking at the infinite dihedral group, and our module is two-dimensional over Z at the moment. And we have already this CR record set up. And we can do two cohomology just using this same, let's try two cocycles first of all, the same record. And here is your result. So in this case, it's a matrix. It's a inside the integers to the 6th power. Let's try to analyze why that is. Now our module has dimension 2. So it's the kernel of A2. So D times L is the dimension in which it should sit. D is 2, that's the dimension of our module, and L is the number of relations that gets used. We are looking at the infinite dihedral group. The relations that are used here are actually encoded in the record C. There are 3 relations. That's first of all the power of the first generator, and then conjugate relations, because in this case I really need to look at G2 of G1. Those are the 3 relations that are used here, and therefore it's 6-dimensional. And it tells you that the two cocycles are a four-dimensional subspace in Z to the 6. Now two co-boundaries. Display. Always prints it in somewhat nicer form. It's also four-dimensional in the same six-dimensional space. And well, if you look at these additive spaces over the integers, it's often not quite so easy to see what they really are. You want to have the quotient. You can get that by additive factor. Oh, well, I have to give it names, I'm afraid. So, two cocycles, CR, CB, two co-boundaries. And now I can go for this additive factor. I have to tell it its characteristic 0. And, well, at least, well, this is an additive group now, and the relations as in a polycyclic presentation that describes it are 2, 2, 2, 2. So it's a group of order 16 in this case. So H2 of G with this module M has order 16. The relations even tell you more. It's an elementary abelian group of order 16. So we could actually do this more explicitly. C2 to the 4. That's what comes out of it. Right. As you can see, computations are getting a bit technical, but you can actually do it. And well, we've now determined two cohomology for an infinite group with an infinite module, found that we have a finite result here. So it's a non-trivial computation that happened, and we can get the result quite readily. Right, and with that, I think we'll have a break now.